in this example, you can see that the integrand is a fraction, or sometimes called a quotient. The integrand is a rational function. You can also see that the degree of the expression on top is less than the degree of the expression underneath, so we can't do division to break this down into simpler functions. Now, we don't have the equivalent of a quotient rule in integration. You know that in differentiation there is a quotient rule. If we had to differentiate something like this function, we call what's on top u and what's underneath v, and we apply a formula. We don't have such a formula in integration, and we can't divide this down, we can't break it down. However, there is a method called integration by substitution which will work for many functions of this type. Not for all of them, of course. There's plenty of them that it won't work for. Integration by substitution happens to work for this particular one. What we try to do is make the denominator into a single term. Try to get this as a single term, then it's much easier to break it down. So what we do is we let u equal the denominator. And the reason why we do that will become clear soon. Usually in these problems we try to make the denominator as a single term. We call it the denominator u. That's one way to break down a fraction. Anyway, let's suppose we call this u. Let's look at du dx. So we differentiate this with respect to x. We get 2x plus 2. Let's rewrite this to make dx the subject. Now you can cross multiply, say du equals 2x plus 2 times dx, and then divide to get dx equals du divided by 2x plus 2. Basically, it all boils down to just interchanging these two. So we get dx equals du over 2x plus 2. So just interchange the 2x plus 2 with dx. Now look at what the integral becomes. Instead of x squared plus 2x plus 2, we write u. Instead of dx, we write du over 2x plus 2. Now, what happens here is we can cancel the x plus 1 with the 2x plus 2. You could, if you want to see it more clearly, we could factorize 2 out of this denominator here. So we get 2 times x plus 1. And the x plus 1's actually cancel out. That must happen if the substitution method is to work. It happens in this case, but it doesn't necessarily have to happen in all cases. Of course, in the examples you will get, it will work, of course. Anyway, this integral becomes the integral of 1 over u with respect to u. And I have the 1 over 2 here, which is a half. That's just a constant term. I can stick the 2 in here, but usually what we do is take it outside the integral sign. So x will disappear if the derivative of the denominator is a multiple of the numerator. So the derivative of the denominator is 2x plus 2, and 2x plus 2 is a multiple of the numerator. It's 2 times the numerator. So that's why our substitution worked. The derivative of x squared plus 2x plus 2 is 2 times x plus 1. Of course, if the denominator happened to be, let's say it was x squared plus 3x plus 2, then the substitution method will not work. Because if we differentiate x squared plus 3x plus 2, we get 2x plus 3. And 2x plus 3 is not a multiple of x plus 1. Now, the integral of 1 over u happens to be ln of u. It's one of the standard integrals. You'll see it in tables. The integral of ln of x, the integral of 1 over x. We cannot get the integral of 1 over x by simpler methods. You know, you can't write x as x to the power minus 1 and attempt to integrate by adding 1 onto the power. The problem here is if we add 1 onto minus 1, we get 0. And if we divide by the new power, well, we're dividing by 0, and we can't divide by 0. So, if the power is minus 1, the integral is ln of x. If the power was, say, minus 2, then we could just do it in this basic way, add 1 onto the power and divide by the new power. So here we get ln of u, and what are the limits? Well, we're after making a substitution, so that affects our limits. We're integrating with respect to u. So the range of values that 1 over u goes over is quite different from the values that this function here range over. This function here is ranging from 0 to 2. The domain is from 0 to 2 in this integral. We can work out these limits by going back to this here, u equals x squared plus 2x plus 2, and letting x equal 0 to find the corresponding u value. That'll give us the lower limit here. So if we let x equal 0 in this, we get u equals 0 squared plus 2 times 0 plus 2, and that gives us 2. So the lower limit x equals 0 corresponds to the lower limit u equals 2. Similarly, for the upper limit, we look at the upper limit in this integral here, which is 2. It's x equals 2. And we look at the value of u that corresponds to it. So it's u equals x squared plus 2x plus 2. So it's going to be 2 squared plus 2 times 2 plus 2. 2 squared is 4. 4 plus 4 is 8 plus 2 is 10. So 10 is our upper limit. So now we can then go and work this out. So we have a half ln of the upper limit, which is 10, minus a half ln of the lower limit, which is 2. We can write this as a half ln 5. Why can we do that? I've used the fact that ln of a minus ln of b is equal to ln of a over b, where a is 10 and b is 2. So ln of 10 over 2 is ln of 5, and I've factored out the half. So this is the answer to the problem. So that's solving this by changing our limits. But we could have just subbed back in for u. Remember, u was x squared plus 2x plus 2. We could have subbed x squared plus 2x plus 2 back for u and just work with our original limits. Plugging 2 in here, we get a half ln of 2 squared plus 2 times 2 plus 2. So the argument of this ln function is 10. This is 4 plus 4 is 8 plus 2 is 10. And then we put down a minus sign and write out all of this again, replacing x with 0. If we replace these x's with 0, we just get ln of 2. So we end up with a half ln 10 minus a half ln 2. Or that's a half of ln 10 over 2. We can take this argument and divide by this argument. So we get a half ln 5. In this example, we want to look at the integral of cos of x over 1 plus sine x with respect to x from x equals a to x equals b. Now, again we have a quotient like in the last example. We let u equal the denominator. That's the usual approach when we have a quotient or a fraction. We work out du dx to get a substitution for dx. The derivative of 1 with respect to x is 0. The derivative of sine x with respect to x is cos of x. You can look that up. And we can rearrange this to get dx. Basically, we just interchange dx with cos x. That's the quickest way to do that. That's du divided by the cos of x. So now our integral becomes cos x divided by 1 plus sine x, which is u, times dx, but dx is now du over cos x. And you can see that this substitution works because everything involving x cancels out and we get a much simpler integral. We have the integral of 1 over u with respect to u, and this is a standard integral. It's ln of u. Now we can either change our limits or we can just sub back in for u and use our old limits. There are two ways we can do this. First of all, I will change the limits. The lower limit here corresponds to this lower limit here, x equals a. So to find the lower limit for the integral of 1 over u with respect to u, we let x equals a in our substitution. So if x equals a, what do we get? We get u equals 1 plus sine of a. And if we let x equal b, which is the upper limit, we get u equals 1 plus sine of b. So the lower limit is 1 plus sine a, the upper limit is 1 plus sine b. So what we do is we write this out, replacing u with the upper limit, which is 1 plus sine b. Then we have a minus sign. We write this out again, replacing u with the lower limit, which is 1 plus sine a. Then we can use one of the rules for logs, which says that log of m minus log of n is log of m over n. So we can take this argument and divide by this argument. So we can write this as a single log term. Now, of course, the other way to do this is to just sub back in for u. U is 1 plus sine x. So we sub back in for u and use our original limits, x equals a to x equals b. So we put the upper limit in, which is b. We get ln of 1 plus sine b minus this again with the lower limit in, which is a, ln of 1 plus sine a, and we can write this as a single log term, as you saw already. It's the same as log of this argument over this argument. In part 2, we want to find in terms of a and b the integral called j, which is the integral from a to b of sine of x over 1 plus cos x with respect to x. Now again, like in part a, we have a quotient. We let u equal the denominator. And if you do that and get the derivative, you will get minus sine of x. Then we need to replace dx. To replace dx, we need to get dx from du dx, so we just interchange these two. That's the result of cross multiplying and rearranging. So we get dx equals du divided by minus sine x. And so we make that substitution for dx, and hopefully everything involving x will cancel out, and it does here. We have a minus sign here. It's like a minus 1 in this denominator. We can pull that outside. We have 1 over minus 1, which is minus 1 outside here. That's just a constant factor. Then we're just integrating 1 over u with respect to u. So we end up getting minus ln of u. Now we can change the limits and all that business and then work this out, or we can just sub back in. Now I'm just going to sub back for u here. So u was the denominator 1 plus cos x. And our limits are from x equals a to x equals b. So we write this out, replacing x with the upper limit, which is b. We get this here. Then we put down a minus sign, and then we write this out again. So we'll have two minus signs together, which will give a plus sign. So we get minus minus, or plus ln of 1 plus cos x. Or, sorry, plus ln of 1 plus cos a. And then we can use the rule for subtracting log terms. Log m minus log n is log m over n, where m is this thing here, 1 plus cos a, and n is this thing, if you want to call them m and n. So it would be ln m over n. It's just written backwards here. Now I did not change the limits here, and in general I don't bother changing limits. I just like to sub back in for u and use our original limits. Now there are some situations where you have to change the limits. In a later video, it's a video titled Integration, Getting the Area of a Circle. We will have a type of integral where it's much easier to actually change the limits than to try and sub back. Okay, you'll see that in a later video. That's probably the only example where changing the limits makes life much easier. But usually I don't bother changing them. And you know, it's quite straightforward just to sub back in and use the old limits. In part 3, we want to show that if a plus b equals pi over 2, then I equals j. Well, this is really just a trigonometry question. If a plus b equals pi over 2, then we can write a in terms of b or b in terms of a. I will write a in terms of b. We can write a as pi over 2 minus b. If we look at the argument of this ln function, we can replace a with pi over 2 minus b. So we get 1 plus sine b over 1 plus sine of pi over 2 minus b. There are two ways we can look at the sine of pi over 2 minus b. One way is to look at a right angled triangle with angle b in it. You know, if this angle is b, then this angle here is just 90 minus b. 90 in radians is pi over 2 radians. You can see that the sine of this angle, pi over 2 minus b, is the side opposite this angle, which I'm calling x, divided by the hypotenuse, which is r. The side opposite pi over 2 minus b is x. But you can see that that's the same as the cos of b. The cos of b is the side adjacent to b, which is x. The side adjacent to b is the same as the side opposite pi over 2 minus b. Sorry, the cos of b is the adjacent over the hypotenuse, x over r. So you can see that we can replace sine of pi over 2 minus b with cos of b. So we can write this as 1 plus sine b over 1 plus cos b. Here's another way you could look at sine of pi over 2 minus b. We can use one of our compound angle formulas. The compound angle formula that we use is sine of a minus b. It's sine a cos b minus cos a sine b. You can look that up in tables. The sine of 90 degrees, or the sine of pi over 2 radians, is actually 1. So we have 1 times cos b. So a is pi over 2. Big B is actually small b here. The cos of pi over 2 is 0, so this goes out. So you could write this in terms of as cos b using the identity for sine of a minus b. Now let's look at the argument of the ln function. So we're looking at j now. We can forget about the ln's. We only have to compare the arguments. If the arguments are the same, then we're done. So I've written this argument out down here, but I've replaced a with pi over 2 minus b. We want the cos of pi over 2 minus b, so again we can refer to this right angle triangle. The cos of pi over 2 minus b is the side adjacent to it, which is y, divided by the hypotenuse, which is r. So it's y over r. But you can see that that's the same as the sine of b. The sine of b is the side opposite b, which is y, divided by the hypotenuse, which is r. So we can replace cos of pi over 2 minus b with sine of b. And now you see these are the same. And we're done. So we've proven that if a plus b is equal to pi over 2, then 1 plus sine b over 1 plus sine a equals 1 plus cos a over 1 plus cos b. And we just get the ln of both of them. So we've proven that I is equal to j. So these are equal. So we can conclude then that I, which is just ln of this thing here, equals j, which is just ln of this.